Hello and welcome to Exponentials Unit 9, Day 1. Today what we are going to be doing is graphing exponential growth and decay functions, talking about their different transformations, and how to write the equation of an exponential using those transformations. You've been probably hearing a lot in the news and online about, this virus taking on an exponential growth pattern. So I'm kind of excited to be able to finally share with you what that means. So exponential functions have a unique equation. Unlike linear and quadratic, the variable is actually in the exponent. So you'll notice that the variable is now going to be up in the exponent place, which means that the coefficient a can never be equal to 0, and b, which is the base of our exponent, can never be 1, because 1 to any power is still 1, and if I multiply the entire thing by a 0, it's just equal to 0. So it creates a nonlinear function. A certain example of an exponential growth, we have amoebas here, but you can just think of it as cells just in general. And exponential growth would be if you have one cell and it divides in two, and then those two cells each divide, so that would make 4. Those 4 cells then each split in half, so that would make 8 total cells, and so on and so on and so on. So clearly, it appears to be growing by multiplying by 2. And so that's the kind of pattern we're going to be looking for when we are talking about exponential growth. So if you have your graphing calculator, this one's already graphed for you. But in your graphing calculator, if you would like to type in the y equals screen 2 raised to the x, so you're going to use the caret symbol. So I can show you on my calculator here. So if you go to your y equals screen, and you type in 2 and then use the caret symbol to make that an x. And then if you go to your table of values, just scroll until you kind of see the same window I do. There you have it. If you look at your y's, 0.5 to 1, 1 to 2, 2 to 4, 4 to 8, 8 to 16, and so on. So it's clearly doubling. And the whole reason why that this pattern is doubling as you increase up the y column is because the base of our exponent is a 2. And so when you go to graph that, this is what we would consider an exponential growth. You always are going to graph from left to right. So if I start here on the graph, it is growing as I read the graph. So that's why it's considered exponential growth. So that base 2 is actually going to be called the growth factor. That is the factor by which it is growing over a specific interval. And that means the y values are being multiplied by 2 for every 1 increase in the x-axis. Now, if I keep this pattern going the opposite way, so obviously at -3, the value is 1/8, which is a very small value. If I go to my calculator again, and I scroll this direction, and I scroll. See how these numbers here are getting smaller and smaller and smaller and smaller? They're still cutting in half. So if I go the other direction, if I start working my way up this way, the values would cut in half. But the question is, if I keep cutting something in half, would it ever equal 0? Well, the answer is no. So here's the tricky thing about exponential growths and decays, is they will never, this part of the graph will never actually go below the x-axis in this case. That x-axis is a very funny word, and that word is asymptote. And I always emphasize the P because it's fun. That is the fancy word that talks about this invisible line that the curve will approach. It gets really, 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 really close, like super close, but it'll never actually touch it, never actually equal it. So it's like this invisible barrier. The y-intercept is going to be the place where it crosses the y-axis, so that y-intercept is going to be a 1. But the thing is, if we have an asymptote on the x-axis, meaning it'll never equal 0. Can there be an x-intercept? No, it does not exist. My professors in college used to write DNE, so feel free to write that as well. Well, domain's easy to remember because domain is going to be all reals, or if you'd prefer writing negative infinity to infinity, that's fine too. It's going to go to the left forever and to the right forever. But your range, okay, the range is dependent on the asymptote. So for this original equation that we just did, the asymptote, remember, was the x-axis, so y equals 0. But it won't always be the x-axis. Eventually, when we get to transformations, it's going to shift around. So in this case, our range is from 0 with a parenthesis to infinity. It's 0 with a parenthesis because remember that parenthesis means not including 0. It will actually, for domain and range, always be parenthesis sets. You won't use square brackets for exponential functions. All right, a different kind of exponential function is called an exponential decay. And we decided to use apples in this explanation. So let's say you start with 32 apples and you gave half of them away, you'd have 16, and then you gave half of those away and you'd have 8, and then you gave half away, it would be 4, and then 2, and then 1, and then all of a sudden you have to start cutting the apples in half. But if you continue that pattern, would you ever get down to 0 apples? And then the answer would be no. You'd have really, really small slices of apples, but you would still be cutting them in half. So I know that that's kind of a weird example to use, but technically exponential decay continues forever. So this one we are going to bring out our calculator for, and we're going to fill in our chart. So if you go to your y equals screen, you can either type in 1/2 raised to the x, or you can do 0.5 raised to the x. So I'm going to do 1/2 raised to the x power, and then I'm going to go to my table of values, and I'm only going to plot the ones that my chart is asking me to, so from -4 to 3. So it looks like I'm going to go 16, 8, 4, so almost the apples example. So this is 1/2 to the -4 power, and that's going to be positive 16. And if you don't trust me, we have learned about negative exponents for a little bit this year, and we learned that they flip. All right, and then the pattern just keeps going. So 16 to 8, 8 to 4, 4 to 2, then 2 to 1, and then it would be 1/2, 1/4, 1/8, and so on. Or if you are not a decimal or a fractions fan, this is 0.5, this is 0.25, and this is 0.125, which I think for plotting points, it's a little bit helpful to have the decimal options. So -1, 2, 3, 4, up 16. So it's going to be 2 from the top. Excuse my dog for a second. All right, -2 up 4. -1 up 2, 0, 1, 0.5, 0.25, 0.15. So this one now, again, remember you read a graph from left to right. Make sure that that right-hand side does not go below the x-axis. So if you read this graph from left to right, it is going in a downwards trajectory. So that is why we call it exponential decay. Domain is always going to be all reals, and actually the range is going to be the same as our growth function, parentheses 0 to positive infinity, bottom to top. The y-intercept is still 1. The x-intercept still does not exist because we have an asymptote there. And the asymptote is a horizontal line. A lot of times mathematicians will represent asymptotes as a dotted line or a dashed line. That asymptote is horizontal, so we should be thinking hoi. And so it's a y equals 0 equation. So your asymptote for exponential functions is always going to be horizontal. Now, if 2 on the last example was our growth factor, then the 1/2, because to get from 16 to 8, I multiply by a half. So 8 to 4, I multiply by a half. That is what we call the decay factor. So now let's talk about just things in general. So when the base was a 2, it was a growth. And then when the base was a 1/2, it ended up being a decay. So let's generalize this. If the base of our function is a number greater than 1, so like our exponential growth function when it was a 2. If the base of our function is greater than 1, so it could be 2, it could be 1.5, it could be 100, whatever. It represents an exponential growth. The graph is going to rise as it goes from the left to the right. But if the base of our exponential, don't think negative, if it is a fraction that falls between 0 and 1, 1/2, 3/4, 0.6, whatever, that's going to give me a decay function, and that's when the graph is going to fall over that interval. And actually, let me go back to growth here for a second, because these numbers are easy to represent. Those numbers are easy to represent, or to recognize that they're growth. But what if I had a base 3/2 raised to the x? That would actually still be considered a growth. Even though it's a fraction, that fraction is greater than 1. All right, so transformations. We have done transformations on all different types of functions so far this year. We have done transformations on square roots, cube roots, absolute value, quadratics, cubics, the list goes on and on. We're going to now add exponential growths and decays into there. So the base, let me repeat this, the base of our exponential is not a type of transformation. That is either your growth or decay factor. So in this first example, the 4 is the base of our exponential. That is not going to be part of our transformation. What is part of our transformation is the +2. So I'm taking that entire exponential function and shifting it up 2. If I am shifting the entire graph up 2, then that means the asymptote has now been shifted up 2. So that's my exponential growth. It will not now go below 2. So y equals 2. So it's actually kind of nice. Whatever your shifting up or down is, that is your equation of your asymptote. It's very straightforward. So similarly, if I take my entire function and I shift it down 3, if I go over my graph, 1, 2, 3, that is my new asymptote spot. And so when I go to graph my exponential, whoop, there's my exponential. It will never go below -3, so my asymptote is -3. All right, well, what if the plus is up in the exponent, where the x is? Well, that's when we're going to start going right or left, and it's just like all of our other transformations. If it's with the x, then it's going to go opposite of what you think. So this is going to be left 1, and this is going to take us right 2. Notice there's no shifting up or down, so our asymptote would still be at 0. We didn't have to shift up or down at all. It was just to the right or to the left. So this one went to the left 1. And this next one went to the right 2. All right, so we have an exponential growth, and I know that because the base is a 2, but that is not what transformation is happening here. This 5 is going to be a vertical stretch. So just like we learned in all of our other functions, if there is a number greater than 1 out front of our function, then it's going to stretch vertically. It's going to make it grow a little bit faster. If we have a 1/2, we call that a vertical shrink. That's V-E-R-T, vertical shrink. And that means it's just going to kind of take a little bit longer to grow. It's going to kind of stretch it out and take a little bit longer. And then the last one here is a negative, and we know that negatives reflect, and we have to think over what axis. So reflect over the x-axis. So reflect over the x-axis, so it would go this way. Cool, cool, cool. All right, let's practice graphing some of these in our calculator. I'm gonna quickly do both. I'll just do the first one with you, and then we'll talk through the second one, but I won't waste your time plotting all those points. So, and feel free to do number 2 if you would like. All right, so number 1, the first thing that I notice is the base is a 2. That tells me that it's a growth. I also notice it has a +3, so that means it's going to be shifted up 3. And then it has a -1, which is actually going to be shifting it to the right 1. If it is being shifted up 3, then that means the equation of the asymptote is y equals 3. So before I even plot anything on my graph, I'm going to go ahead and draw in my asymptote line, because I know my graph cannot go below that spot. Then I'm going to bring up my calculator. You guys can bring out your calculator at home. Go to your y equals screen. And we are going to type 2 raised to the x minus 1. And then arrow over and then hit +3. Go to your table of values. And we're only going to graph the ones that we can fit. So my graph goes up to 24. Okay, so I'm going to go from, it looks like I'm going to graph from maybe like -1 to 5. I think that should be plenty. So from -1 to 5 should be plenty. So making an x and y list, hopefully you have this on your calculators at home. Just going to list this down. This is essentially my work. So I'm going to plot these points, make a nice curve through the points. Remember, don't let your curve go below your asymptote line. All right, so -1 up 3.25, so it should be just above our asymptote. 0 up 3.5, which I know is almost looks in the same spot as the other one, but we'll do our best. 2 up 5, 3 up 7, 4 up 11. So notice the space between each dot is getting bigger and bigger. That's because it's exponentially growing. And now we're going to connect our dots. Don't let this left-hand side go below the asymptote. And we're just going to put arrows on each end. Beautiful. All right, we created a table of values. State the domain. Domain's easy. That's all reals. And range is actually pretty easy too, because we already said the asymptote is at 3, so it's parenthesis 3 to infinity. So number 2, I'm not going to actually graph this one, but I do want to talk about it. The 3/5, think about that. That is the base of your exponent. Is that greater than 1? Or is it between 0 and 1? Well, 3/5 is 0.6. So this would be a decay function. It would be a decay. It would be shifted down 1. So the equation of the asymptote would be y equals -1. So we would have our asymptote line, and then we would have our exponential decay. All right, number 3, it says write the equation, the results when, we're going to call this something called our parent function. It is an exponential growth, and we are going to take that parent function and we are going to write a new equation that is being shifted to the left 2 and up 4. So if I take my parent function and I want to shift it left 2, that would be a +2 with the x, and then an up 4 would be a +4 after it. So that's all we're doing in this section, is writing the equations. So the next one is right 3 and up 7. So start with your parent function, and then we want to manipulate it by shifting it right. So that would be a -3 up with the x, and then a +7 to shift it up 7. Vertically stretching by a factor of 3, so vertically stretched by 3, here's our parent function. If I want to stretch that, I need to put a 3 out front, and then I want to shift it down 1. And then this one's left, reflected, and down. So start with your parent function. I want to go to the left, so that's a plus 3. I want to go down, which is a minus 5, and then the reflected, you have to put parentheses around the 4 and put a negative out front. The base of your exponent will never be negative, so you always have to put parentheses around it to represent that reflection. All right, the population that initially has 20 birds and doubles every 10 years. So the fact that it's saying doubles, that means we are multiplying by 2. If we are multiplying by 2, okay, it's growing by doubling every 2 years. It cannot be a straight line. And obviously option 2 here is a decay, because that means the birds are like dying over time. We want the ones that are growing, doubling every 10 years. And we initially started with 20 birds. So in the year 0, we started with 20 birds. It's gotta be option 3. All right, and then last one, the range of the function defined by y equals 5 to the x. This is exponential growth with an asymptote of y equals 0. So if I was to draw a sketch, it would look like all the rest of the exponential growths, and it wants to know the range. Range is bottom to top. Range would be from 0 to infinity with parentheses. Now remember that parenthesis means not including. So that means these two are out. Those inequalities are equal to. We want the one that's not equal to 0. Okay, so y is less than or y is greater than 0. And it would be all y values greater than 0. All right, see you next time for day 2. Bye.